So, this is a lesson on heating and cooling curves. A heating curve is a graph that shows how temperature changes when you add heat to a substance. And most heating curves have the same shape, regardless of the substance. So it could be water, it could be sulfur, it could be iron, it could be carbon dioxide, but the curve will have the same shape, and we can get some key information about the substance by reading the graph properly. So the goal of this lesson is to have you understand some key features of heating curves and their opposites, cooling curves, so you can get that information. A heating curve shows what happens to temperature as you add energy to a substance, and the substance gets heated and melts and is heated some more and boils and is heated some more. So the substance is going to go from solid to liquid to gas over the course of the heating, and a predictable thing will happen to the temperature of the substance. Temperature is the dependent variable. We're measuring what happens to temperature as we intentionally add heat to the substance. So adding heat, or the amount of heat added actually, is the independent variable. Temperature appears on the y-axis as the dependent variable. You can measure in degrees Celsius or in Kelvin. You could also measure in degrees Fahrenheit, although that's not typical. And energy added is the independent variable, and you would measure the amount of energy added in metric units of joules or kilojoules, or sometimes in chemistry we still use calories. The y-axis is always temperature, but the x-axis could actually be measured with time. If we knew that heat was being added to the substance at a constant rate, then we would be measuring time, 10 seconds, 20 seconds, 30 seconds, 40 seconds, and essentially that would be equivalent to some constant amount of energy for each 10-second interval or whatever. So as long as we knew that the energy was being added at a constant rate, we could measure the time instead of actually measuring how much energy. Sometimes that's easier. And sometimes you'll see time on the x-axis then. The first thing that you should know about these heating curves is that they always have the same shape. So if I make a heating curve, it's always going to start off low, where the temperature is low. It's going to have an upward slant, followed by a plateau region, followed by another upward slant, followed by another plateau region, which is typically longer than the first one, followed by another upward slant. So this is a typical shape for a heating curve. It has these three segments that show an upward increasing slope, and we have these two plateaus, these two positions where the temperature stops changing. The temperature stays the same for a while. Temperature is going up, 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 up. Temperature stops changing for a while. Temperature goes up, 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 up. And temperature starts changing for a while. And then the temperature goes up, up, up. That is predictable for a heating and a heating curve. The substances will go through the same series of temperature changes while they are being heated. So the shape of the curve is not going to change. Now, when I look at the curve, I should be able to tell what states of matter are present. So when the substance is at the low temperature, at the very beginning of a heating curve, the substance is generally in the solid state. And I heat that solid for a while, and it's eventually going to get to a point where the molecules are vibrating so quickly that they break their bonds and form a liquid. And that's what's happening at this plateau. The solid will be changing to liquid. And after all of the solid has changed into a liquid, then the temperature will rise again. But that can only happen after all of the melting is done. So when all of the melting is done, there's no solid left, there's only liquid. And then the temperature will rise again for a while until you get to the point at which the liquid molecules are vibrating and rotating so violently that the rest of the bonds break. And so now the liquid is going to change into a gas. And while the liquid changes into a gas, the temperature is going to be stuck for a while. And then after all of the liquid has been converted to gas and there's no liquid left, then the temperature of the gas can rise. And so at the slanted portions of the curve, you just have one state of matter. The lowest being solid, the middle one being liquid, and the higher one being gas. During the flat portions of the curve, you have some change of state occurring. The lower one will be solid to liquid. The higher one will be liquid to gas. Solid to liquid, of course, is called melting, and liquid to gas is called boiling. All right, so you should be able to identify the states of matter that are present at each segment of the curve. So the first segment, from A to B, we just have solid. From B to C, we have solid converted to liquid. By the time we get to C, all of the solid is gone. So from C to D, we just have liquid. From D to E, the liquid is melting, so we have, the liquid is boiling, so we have liquid and gas present. When all of the liquid has boiled away, then we only have gas, and so from section E to F, or from points E to F, we have a gas. Now, we're adding energy to these molecules, and as a result, the kinetic energy or possibly the potential energy of the molecules will be changing. So there are portions of the curve where we can identify that kinetic energy is changing and portions of the curve that we can identify where potential energy is changing. Now, a key thing that you should know is that when the temperature is constant, you're going through some kind of a change of state. So during a change of state, the temperature is constant. So when the solid is changing to liquid, the temperature stops changing. When the liquid changes to gas, the temperature stops changing. And that tells me that nothing's happening to the kinetic energy of the molecules there, because temperature is directly proportional to kinetic energy. We're going to use this Greek letter alpha to represent proportional. And so temperature is directly proportional to kinetic energy. If temperature is directly proportional to kinetic energy, when the temperature is constant, the kinetic energy is constant. So in those flat portions of the curve, the kinetic energy is not changing. And in the slanted portions of the curve, where the temperature is rising, since temperature and kinetic energy are directly proportional, it must be that kinetic energy is rising there. So since the temperature is rising, as we go from A to B, the kinetic energy must be going up as well. Since the temperature is rising as we go from C to D, the kinetic energy must be rising as well. And since the temperature is rising as we go from E to F, then the kinetic energy must be rising as well. Places where temperature goes up, kinetic energy is correspondingly going up. Places where the temperature is flat, constant, not changing, the kinetic energy won't be changing. So if you're asked where is the kinetic energy changing and how, you will always be looking for a portion of the curve where the temperature is changing. And if the temperature is going up, then kinetic energy will be going up too. Potential energy changes don't correspond to temperature. Potential energy changes correspond to freedom of motion. So the potential energy will correlate with molecules that have more freedom to move around. So if I have a gas with the ability to vibrate, rotate, and translate, that has a lot of freedom to move, and so the potential energy of those molecules is higher than the potential energy of the liquid molecules that can only vibrate and rotate but not translate. And the potential energy of the liquid molecules is higher than the potential energy of the solid molecules that can only vibrate. So when we're going through a phase change, when bonds are breaking, that's when the potential energy is going to be going up. When bonds are breaking and we get additional freedom to move, then that's giving the molecules more potential energy. And so from point B to C, the potential energy is going up because the bonds are breaking. When you go from solid to liquid, molecules are getting greater freedom of motion. And from section D to section E, from point D to point E, the potential energy is going up there as well, because when liquid molecules go to gas, bonds are broken, and gas molecules have more freedom of motion. It's probably worth noting at this point that the molecules are gaining energy the whole time. Energy is being added to the molecules from some external source. So the molecules are being heated in a test tube with a Bunsen burner, or the molecules are being heated in a beaker with a hot plate. The molecules are only gaining energy during the heating process. This is not an example of conservation of energy because the molecules are not an isolated system. The molecules are receiving energy from an external source. If I include the hot plate and the water in the beaker, then that could be considered an isolated system. Whatever energy is lost by the hot plate is gained by the molecules. But if I'm only considering the molecules, it's not an isolated system, so I would not assume that the energy is traded off. The energy is only being gained. I guess what I'm trying to get at is that on the roller coaster, when the marble went downhill, it lost potential energy, but it gained kinetic to replace it. That's not what's happening here. The solid molecules are gaining kinetic energy. When they melt, they're gaining potential. The liquid molecules are gaining kinetic energy. When they boil, they're gaining potential. Then the gas molecules are gaining kinetic energy. There's no trade-off. It's not that when you're gaining kinetic, you're losing potential. You're gaining the whole time because something somewhere else, the hot plate, is losing the whole time. So overall, there's energy conservation, but not for the molecules. The molecules of whatever substance this is are gaining some kind of energy all along the graph. Finally, the graph is useful for reading some key pieces of information. So I can read the melting point off of the graph. It's the temperature at which the substance melts. So it's the Y value that corresponds with the plateau that I see from point B to point C. So this temperature would be the melting point. And this temperature for the second plateau, where boiling is occurring, is going to be the boiling point. So I can read those pieces of information off of the graph. This thing, delta HFUS, is called the heat of fusion. And the heat of fusion is the amount of energy that's required to melt something. Fusion and melting were synonymous terms, but we don't typically call melting fusion anymore, but it's still kind of stuck to that delta H there. So the heat of fusion is the amount of energy that's required to melt something. Now energy is read off of the x-axis. So the amount of energy you need to melt this stuff is the amount of energy it takes to go from B to C. So if I could read that value off of the graph, subtracting these two x points to figure out the difference between them. The difference between the energy value when the melting starts and when the melting ends is called the delta H of fusion, the heat of fusion. And the heat of vaporization is the one that corresponds to boiling. So when the substance starts to boil and when the substance stops boiling, the difference in energy between those two positions is called the heat of vaporization, which we symbolize with delta H VAP. So the heat of fusion is typically a smaller number, so that plateau is shorter than the heat of vaporization. Because in order to melt something, you just need to break some of the bonds. Breaking some of the bonds breaks down the structure of the solid and it allows some molecules to rotate and flow past one another. But you don't have to break all of the bonds to do that. You don't even have to break most of the bonds to do that. You just have to break some of the bonds to do that. But when you want to go from liquid to gas, you have to break all of the rest of the bonds because gas molecules are not bonded together. And so if you want to break all of the rest of the bonds between the liquid molecules, that's probably going to take a lot more energy. So generally, the heat of vaporization is a number that's bigger than the heat of fusion. We can see all of this in reverse order if we look at a cooling curve. So a cooling curve is a graph that shows what happens to the temperature of a substance as that substance is cooled and it changes from a gas to a liquid to a solid. So a heating curve starts low and ends high. That's what we saw up here, starts low and ends high. And over here, we're going to see that it starts high and ends low. And so if it starts high and ends low, we're going to see a slanted portion and then a flat and then a slanted portion and then flat and then slanted again. It's always those same 5 segments: slanty, flat, slanty, flat, slanty. And it's either going to be headed in the upward direction, slanted, flat, slanted, flat, slanted, or it's going to be headed in the downward direction for a cooling curve, slanted, flat, slanted, flat, slanted. Here I'm starting at a high temperature. My substance is a gas to start off with, and then from points A to B, that gas is cooling off. So its kinetic energy is dropping. And then at point B, it starts to condense, and the gas will change to liquid. And so when all of the gases change to liquid, then there will be only liquid left, and that liquid can cool. While the gas is changing to liquid, bonds are forming, and the molecule is losing the ability to translate. That's a type of motion. So it's losing some freedom of motion. So potential energy will be dropping. When all of the liquid is formed, none of the gas is left over, then the liquid will cool down. And so when I see the temperature dropping, I know that means the kinetic energy is dropping along with it. So from from point C to point D, I have just a liquid whose temperature is dropping, so the kinetic energy is dropping, the molecules are slowing down. At point D, the liquid starts to solidify to form a solid, so that's freezing. And when freezing happens, bonds form, and so potential energy is dropping. And then at point E, all of the liquid has been converted to solid. There's only solid left, and the temperature is dropping from points E to F. And so since the temperature is dropping, the kinetic energy is dropping. And this is just the opposite of what we saw here. First it was kinetic energy up, then potential energy up, then kinetic energy up, then potential energy up, then kinetic energy up. And here we're seeing the opposite. Kinetic energy down, potential energy down, kinetic energy down, potential energy down, kinetic energy down. All right, overall shape, same, but in the opposite direction. States of matter, also opposite, gas to liquid to solid instead of solid to liquid to gas. When is kinetic energy changing? When the temperature is changing. How is it changing? Well, temperature is dropping, so kinetic energy is dropping. From points A to B, from points C to D, from points E to F, the temperature is dropping, so the kinetic energy is dropping. When is potential energy changing? When bonds are forming. Where does that happen? From B to C, we're seeing condensation. Bonds are forming, so potential energy is going down. From D to E, we're seeing freezing. Bonds are forming, so potential energy is going down. And finally, the melting point and the boiling point. Well, shouldn't they be called the condensation point and the freezing point? Sure, but those are the same thing. For example, if this were water, water condenses at 100 because water boils at 100. Those are the same temperature. So this is the boiling point or the condensation point. We just don't typically use that phrase. We always call it the boiling point, even for condensation. And down here, we would see working backwards to the y-axis to get to the freezing point. Should I call it the freezing point or the melting point? It doesn't matter. Those are the same thing. So I can say the freezing point of water is 0, the melting point of water is 0. If this was water, that plateau would be happening at 0. What is the heat of fusion? The amount of energy required to melt something. So what will I see on this curve? On this graph, I'll see the amount of energy that I have to remove to freeze something. So whatever the difference is between these 2 points, that would be the heat of fusion. And heat of vaporization, well, that's the opposite, or that's the amount of energy required to boil something. So here, it's the amount of energy that I have to remove to condense something. So the difference between this point and this point, this distance here, is the heat of vaporization. We can get the same information from a cooling curve that we can get from a heating curve. So even though when we're heating it, we're getting the melting point and the boiling point, and when we're cooling it, we're getting the condensation point and the freezing point, those are correspondingly the same thing. Boiling point and condensation point are the same, and freezing point and melting point are the same. Heat of vaporization that you get for boiling is the same as what we would call the heat of, I guess, condensation. And the heat of fusion for melting is the same as what we would call, I guess, the heat of freezing. Possibly, I think that could be called, but we don't usually refer to it by those opposite terms. So even when it's condensation, we'll call it heat of vaporization. It's just that you're removing the energy instead of putting it in. And even when it's freezing, we'll call it heat of fusion. It's just that you're removing the energy instead of putting it in. Here's an actual graph for water. I like this one because up here we see some molecular images which show what the molecules are like. So in this section of the curve I have solid. So up here correspondingly I see a solid. And in this section of the curve I have solid changing to liquid. Melting is happening. So here I see a combination of solid and liquid. And here all of the liquid has been formed. There's no solid left. So up here I see liquid and no solid. And here I see liquid changing to gas, and up here I see liquid molecules changing to gas molecules. And finally, when all of the liquid is gone and I only have gas left, I see just the gas molecules there. So that's nice. It gives you a good idea of what is happening to the molecules during the process. Ke is going up, Pe is going up, Ke is going up, Pe is going up, Ke is going up. I can read the melting point for water off of this graph. Melting is happening at 100, at 0. Melting point happening at 0. And I can read backwards from the higher plateau to see that the boiling point is 100. I can read off the x-axis the difference between this number and this number. 160 minus 80 is 80. This is in calories. The heat of vaporization of water is 80 calories. I had to put that scale on there. It did not come with the graph the way it was. And since I know the heat of vaporization of water is 80, and the heat of fusion of water is 80. Have I been saying vaporization? I apologize. The heat of fusion of water is 80, and the heat of vaporization of water is 540. So I put in this little break symbol to show that there must have been a break in the graph there, because this distance is not correspondingly large enough. It's not big enough to show 540, so there must be a break in the scale there. It takes 540 calories to boil 1 gram of water, and it takes 80 calories to melt 1 gram of water. So this graph is for 1 gram of water. If you had, real values on the x-axis, you could read the heat of fusion. It's this difference, and the heat of vaporization. It's this difference. This is what that graph really looks like then. We can see here this difference. We go from 20 to 100, so this difference is 80. And we can see here we go from 200 to 740. This difference is 540. So that's the real length of that second plateau. See, it's a lot longer than the first one, because to break all of those bonds in the water molecules in order to change them to steam takes a lot more energy than just to break a few of the bonds to melt it. So this is the heat of vaporization for water, which is 540 calories. And here, from 20 to 100, we have the heat of fusion of water, which is 80 calories. The melting point is at 0 still. The boiling point is at 100. What if it's not water? What if it's a different substance? Well, then I can read the information I need. The melting point of this substance, whatever it is 60. The boiling point of this substance, whatever it is 120. The heat of vaporization is 30 minus 10, so 20. I'm sorry, that's the heat of fusion. I think I've said that wrong a couple of times today. So 20 what? Look at the units, kilojoules. And over here, we would see the heat of vaporization, and that would be 80 minus 50 equal to 30 kilojoules. So you can get the information that you need from a graph of this type, a heating curve. Here's a cooling curve. So here I have gas, and gas changing to liquid, and then liquid, and then liquid changing to solid, and then solid. And I can read the point at which the gas condenses is 218. I call that the boiling point. And the temperature at which the liquid freezes, we could call the freezing point or the melting point. We don't generally use the term condensation point. We use boiling point for that number, but you'll often hear freezing point and melting point used to describe the same number. In this graph, the kinetic energy of the molecules is dropping. Then as they condense, the potential energy is dropping. And then for the liquid, the kinetic energy is dropping. And then as they form bonds to freeze, the potential energy is dropping. And then as the solid cools off, the kinetic energy is dropping again. This is condensation happening over here at this plateau, and this is freezing happening over here at this plateau. On this graph, I can't read the heat of fusion or the heat of vaporization because it's not, we're not measuring the energy removed from the substance directly. We're assuming that energy is being removed from the substance at a constant rate. And so by measuring time, we're substituting that for the heat of, for the amount of energy removed. But if I knew how much time it took for the substance to condense, and I knew the rate at which energy was being removed, I could get the heat of fusion from that. And if I knew how much time it took to freeze, and I knew how much energy was being removed during that time, I could find the heat of vaporization. And you can go in the opposite direction as well. Draw a cooling curve for a substance. All right, so I'm going to draw a cooling curve. So that means that I have temperature in degrees Celsius on my y-axis, and I'm going to have heat removed because it's a cooling curve on my x-axis. Now my y-axis is in degrees Celsius because I can see that in the problem. What is my x-axis in? It looks like calories. Okay, so my x-axis is going to be measured in calories. The graph always has the same shape. This is a cooling curve, so it starts high and ends low, slants downward, then plateaus, slants downward, then plateaus, and slants downward. They want me to draw a cooling curve for a substance with a boiling point equal to 90. I don't really need to make a scale. I just need to label that point 90. And freezing point equal to 40. So that second plateau happens at 40. Again, I don't need to make a scale. I just need to label what that Y value is. It has a heat of vaporization equal to 100. Heat of vaporization is this corresponding distance. So the heat of vaporization is 100. And I kind of anticipated that going in. I knew the second one should be shorter. So the heat of fusion here, it says, is 50. Calories. Identify places where the kinetic energy changes and how it changes. So anytime there's a temperature drop, there's going to be a kinetic energy drop. And anytime there's bonds forming, there's going to be a potential energy drop. Identify places where potential energy changes and show how it changes. So bonds are forming here, so potential energy is dropping. And then finally, it says identify the states of matter present at each portion. Things can get a little crowded, so that's why sometimes it's helpful to label with points. A, B, C, D, E, F, and then you can say from A to B, you only have a solid, and from B to C, you have solid changing. Oh, sorry, backwards, I'm thinking heating curve. From A to B, I have a gas. From B to C, I have a gas that's condensing to liquid. From C to D, I have a liquid. And from D to E, I have a liquid changing to solid, so I have freezing. And from E to F, I just have solid. All of the liquid is gone already. That's it. Very good.